Hello everyone, my name is Mads Barami from Wolfram Research. Welcome to this sixth session of our live coding series with Andreas Lauschke. If you are joining us for the first time, Andreas has a master's degree in financial mathematics from the Technical University of Berlin, and he has been using Wolfram technology for more than 26 years. During these sessions, Andreas will be live coding the key features of Wolfram Language that every data scientist should be able to manage properly. During the first session, he focused on the operator notation and showed simple applications. The following 4 sessions, Andreas discussed association, dataset, query, and web-based data scraping. You can find his lecture recordings on the Wolfram YouTube channel. Andreas has also updated his notebooks together with some homework on your Wolfram community. Today, Andreas will give us an introduction to outlier detection method. This will be part 1. With part 2 of outlier detection method to follow in the next session. Without further ado, let us welcome our instructor, Andreas Lauschke.
Well, hello everybody. Yes, thank you for the introduction, Mads. Hello everybody and welcome to my 6th session of the live coding sessions for the data scientists. Today I'll be talking about outlier detection methods, and also next week, perhaps also a third week, we'll be talking about outlier detection methods, and I will start today with some simple, quick methods that come intuitively, that come naturally. They're not totally scientifically sound yet. We'll go more into those a little bit later, but I want to show you some basic building blocks like Legos that allow you to build something on your own or to understand the structure a little bit better. I think it's important to have some Swiss Army knives or some jackknife solutions that allow you to do a quick analysis on your own so that you understand the more involved methods afterwards. And in particular, I'll be looking at the k-nearest neighbors and also at clustering. The k-nearest neighbors have vast applicability. They're used as submethods for many other things. For neural networks, for artificial intelligence, for optimization, and the built-in function predict and classify have them as submethods. And clustering, if you think about outlier detection, then pretty quickly you can understand that we are really in a clustering problem. What's not an outlier is an inlier, and the inliers should form a cluster. And the outliers should form clusters. One outlier alone can be a one-element cluster, but it's a separate cluster because it's not an inlier. And you can have several outliers that together form a cluster. Or you can at least have one-element clusters. For example, if you have one element above the data set, one below, then these two outliers certainly cannot be in one cluster, but there can be 2 one-element clusters. So we're really talking about clustering here because outlier detection can be understood as a subproblem of clustering. And then I'll show some diagnostic visualizations. The kernel has several functions built in that we can use and then display nicely in the front end. And the next session I will be focusing on find anomalies. That is new in M12, and I will start with a mathematical intro and then some simple applications, advanced applications, and discuss problems. All right, let's jump right into, and I'd like to begin with a big warning, with a big caveat about outlier detection, because it's frequently done very wrong. I'd like to emphasize today's session is about outlier detection methods, just the methods. And I want to emphasize it's not the case that you should always remove an outlier. Oftentimes the outlier can have the most meaningful information, and what to do with an outlier is always the judgment call of the model builder. You're not just throwing an outlier out because it's so far out there. You always need a scientific reason to remove an outlier. It's always a scientist's judgment call. It's so far out there is not a valid reason. There can be reasons for that value being so far out there. The removal decision has to be a judgment call of the scientist. So just because it's an outlier doesn't mean you should throw it out. There can be good reasons for something to be a legitimate outlier. And in the following, I'll show you a couple of points, a couple of examples, and want to discuss this a little bit further. A seemingly outlying observation may not really be an outlier. You may think it is, right? But you don't really know the model yet. You haven't understood it yet. You haven't even built it yet. And what if nature functions according to a process that you just haven't understood yet? You build your model, you think you understand it, but you do know that every model is always just an approximation. And what if it contains highly localized behavior? So in this following hypothetical example, I'm creating a highly localized behavior with a pole, and look at this plot. So here you see, for example, a plot that at first sight it looks like a sine function, but it really isn't. This is part of nature. This is part of the reality. And if you just drop it, if you just throw it out, then, well, you're getting misled that the real model is something like a sine function and you're done with that. No, it's actually this very outlier here that points you to the fact, look, this is not nature. This is not reality. This is nature, right? So don't throw something out just because it's far out there. It can actually be the item that causes you to detect that that your model is insufficient. And you cannot just throw something out as a measuring error. It reminds me of a joke that my physics teacher told us in 9th or 10th grade, that you can just, if you just throw out certain measurements because you don't like them, because they don't fit into the overall picture, then you're making a big mistake. And the joke he gave us was, okay, this is how the physicist makes a proof, a mathematical proof for a theorem. So here's an example. So he said that all odd numbers are primes. All right, let's look at this proof by observation. 1, true. 3, true. 5, true. 7, true. 9, measurement error. 11, true. 13, true. 15, measurement error. 17, true. 19, true. Okay, we're done. We had 2 outliers. We throw them out. But in general, we can conclude all odd numbers are primes. So with this joke, I want to underscore the point that don't just throw something out that doesn't fit into the overall picture. It may actually be the most meaningful information to show you that your hypothesis or your model is wrong. Okay? Next, I want to make the point that a lot of manipulation is also done with outlier removal. So, for example, some companies fire employees that just don't fit in with the crowd, and those people usually don't get an exit interview. But those people may be the ones who have the most relevant information about what the company is doing wrong. That's why they disagreed so many times with their coworkers. And I think especially they should be heard. It's the people that you fire that should get an exit interview and that should be heard. If you don't, then you're creating an echo chamber. And this can be done intentionally or unintentionally. But this is how you create them, right? If you pursue it because you're trying to run a company where you want to have an echo chamber, or it can really happen unintentionally, right? These are the 2 flavors of this. So keep in mind, a lot of manipulation is done with outlier removal. So don't just throw something out because it's out there. So if you look at this a little bit more strictly speaking, an outlier should be classified as such based on a scientific reason. And the fact that it's out there is merely a manifestation of an underlying reason that disqualifies the observation from being in the group to begin with, right? It's not an inlier, and you need to have the scientific reason, and the fact that it's out there is just a visible manifestation of the fact that's not part of the group. And that reason should be an exogenous factor of the modeling environment. So I'm giving you two examples now. So for example, you're measuring something and your measuring equipment gives you different readings because today the power company pumps 200 volt into the grid and not 110 volts. Okay, that's an exogenous factor. And in this case, it's fine to remove those measurements, but not because the measured readings are different, it's because the measurements aren't valid to begin with. The fact that now it's 200 volt means that your measuring equipment shows you something wrong, right? It's calibrated for 110 volts. If you give it 220 volts, well, garbage in, garbage out. You cannot rely on these measurements. So here it's totally fine to remove them, but not because they're outliers. It's because the measurements aren't valid to begin with. So in another case, we're saying your measuring equipment gives you different readings today because it's super hot, right? It's super hot in the lab where you're making them and the air conditioning is broken. So now all your metal sticks are a millimeter longer, right? You know that metal expands with temperature and therefore you now measure something that's different because of the temperature of the environment that you're sitting in. And here it's not okay to just remove these outliers because you know that your model needs to take temperature into account. If you just remove them and then you proceed with a temperature-free model and remove the outliers, then you're building a bad model. So the solution is you build a model with an additional dimension that is temperature, right? At this point, you know already that the temperature-free model is a bad model. So you have to build a better one. And very often, the outlier may have the most salient information. And oftentimes, it's actually the outlier itself that points you to where the problem is. Sometimes you're actively looking for outliers, right? What if you have a big office building and every room has a thermometer and you see that one is super hot and you know that you have a fire in the building? Well, that's probably the room that's on fire. You're not going to discard that outlier. Or a fuel tank for tank 5 is coming down rapidly. That's probably where your plane is leaking fuel. Or fraud detection works like that, right? You want to find the guy whose financial transactions are sufficiently dissimilar to what everyone else does, right? It doesn't make him a fraudster, not necessarily, but you're looking at something that is dissimilar to everyone else. At this point, you just want to detect this guy. What you do with it is another matter, but it's the outlier here that identifies the guy that you want. So remember, never remove an outlier without a scientific reason. Don't remove outliers just for being outliers. And you need a scientific reason that justifies it. And it depends on the purpose of the model, right? Do we want to find problems? Or do we want to build a model with homogeneous data, meaning only the inliers? And sometimes you want homogeneous data and sometimes you want to diagnose problems. But certainly there can be very good scientific reasons to remove an outlier. You don't want outliers that can justifiably be removed to distort a good model, right? We don't want to keep someone who we know is problematic and draws down the entire model itself. In that case, you certainly have a good reason to remove it, because without the outlier, you have a good model. And when in doubt, maybe this question may help you. You ask yourself the question, is the suspected outlier really abnormal or unnatural? That may help you on your judgment call whether or not something is an outlier. Okay, so now let's look at some simple examples. The first section, I just want to use some quick and simple tools that you can look at that give you a quick idea. So this is bordering the nearest neighbor idea. So the following is not necessarily precise science, but I want to get you going on something simple. So one thing I like to look at is nearest, and nearest looks at the data in a nearest neighbors context. And then I'll also talk about central feature and find clusters later on. So we should expect that an outlier have a large distance to its nearest neighbor. So what I'm doing here is that I'm creating 20 random numbers between 1 and 10. And then I'm adding the number 32. That's my outlier. And I'm now going through this entire list and compute the nearest neighbor of them. I obviously have to delete the element that I'm currently looking at from consideration, because every element has a distance of 0 to itself. So I have to throw out that element itself, but then I can just find the distance to all the other ones. And we see that in this case we have a distance of 22 for our number 32, right? It's that 10, that's the nearest neighbor, and 10 plus these 22s are 32. And sounds fairly simple, right? But this is getting more involved in a moment. And keep in mind that such a very simple check, imagine you have millions of data items, right? Not just 21 here. So it's a very simple check that you can use, and it should be fairly intuitive. We should expect an outlier to have a large distance to the nearest neighbor. But what happens if we add just one more, all right? What if now we're also adding a 33 here? So at this, in this case, we're having a problem, because the nearest neighbors for 32 and 33 are each other. So you see that all distances here are 1, right? Even though there's a big gap here from 10 to 32. So we're not doing the right thing here. The number k of the k nearest neighbors concept here is too low. We're just using 1, even though we have potentially 2 outliers. So we need to increase the number of neighbors that we're looking at. And here I've set it to 2. And suddenly our method works again, right? We see a 22 here and a 23 here. And the other ones are simply 1s. But we can also go higher, right? Instead of 2, what if we use 20? Now we're looking at the 20 nearest neighbors. And this seems to be robust. We can clearly see that the high distances are down here at the 32, 33. These are the outliers, right? And the other ones have low numbers for most of it, but they have high numbers in the last two, right? 31, 32, 25, 26. So all this points us to the fact that the last two are probably our outliers, right? This is the k nearest neighbor concept, and it's very important to set a sensible number k for this, right? If I set it to 1, then I can fool the method already by just using 2 outliers that are themselves close together. So there is more math involved in this that I cannot go into, but I think a nearest neighbor concept is an intuitive first way to look at this. Okay, all right. So this means with the simple nearest neighbor approach, we're looking at one outlier and just one. 2 outliers can totally ruin this approach already. And if it's more than 1 outlier, we have to increase the number of neighbors to avoid these false traps. And that's why it's called the k nearest neighbor methods. Okay. I already mentioned, in a way, we're bordering on clustering here. We're looking for clusters of outliers and inliers. And outliers ought to form clusters and be just a 1-element cluster. And so ought the inliers. And if the outliers don't form clusters, we can't really consider them outliers. And in a future session, I think I should cover clustering theory. It's a very important key concept in modern day data science. And I really need to cover some of this and k-nearest neighbors and regression. They're all related, and we are already applying these principles here for the very specific application of outlier detection, right? It's really a very specific application of more general concepts. Okay, central feature and fine clusters. I think I can better show them with larger examples, not just these 22 numbers here. So I'm waiting with them. I find them not so good with single outliers, and they can be very powerful for several candidate outliers. Okay, next, I'd like to talk about the box plot and the distribution chart. So a box plot, in descriptive statistics, the box plot is a method for graphically depicting groups of numerical data through their quartiles. I think I took this directly from the Wikipedia page. Box plots may also have lines extending vertically from the boxes, and they're called the whiskers, indicating the variability outside the upper and lower quartiles, and so on and so on. I'm not going to read you the entire thing, but what's important is that it's non-parametric, right? We don't need any additional parameters, and they're based on quartiles. And quartiles contain a lot of inherent information already that makes the box plot a very powerful diagnostic visualization. In a way, I think of it as a summary of the histogram. And all right, here is the Wikipedia definition for you. Please have a look at that. So what does it look like? So using the data that we had above, the 1 to 10 plus then 32 and 33, let's look at them. So if we do a regular box whisker chart, then we are getting a display like this. You can see that you have the total range indicated by the whiskers and the bars, and you see the median value here, and you see the quartiles, right? Here you can you see 4 segments here. Those are the 4 quartiles. And I just love how in the mathematical system we're getting a very intelligent hover. This is again a basic summary with the numeric data. I think of such a hover as a data card. That's just my own terminology. You get a data card that comes as a hover together with this plot, and you can specify that you want to focus on outliers. You can put that here in the second argument, and you will see that when you specify outliers, the suspected or the presumed outliers are removed. You can see that the whisker here ends down here at what is that, 10 or 11, and then we see the outliers up here. So we see the 32 and the 33 here as outliers, but once they were diagnosed as outliers, they were removed so that we see a much shorter quartile here down where we show the real box plot. Okay, and we can provide several of these specifications. I've copied this table directly from the help browser, and let me show you them when we look at all of them. These are the 6 that we have on the table above there, and I'd like to encourage you to look at the help browser. It has so many options to style it, to define things, to display it, the styles, the colors. Look at it. You get a very detailed explanation, and you get specifications for how you provide the data, what you want to show. Very comprehensive documentation in the help browser. Have a look at it. Okay, so here we see the outliers as a specification. I had already showed you that. You can specify median, then you just get the median here as a white bar in the middle. You can also specify mean, and then you get the mean as an additional black bar wherever it is in the plot, and you can show it as a diamond, and so forth, right? And again, there's themes, there's color specifications, and many other things. Okay, so let's focus specifically on the outlier specification here. And I'm taking the following directly from the help browser. I think it's a very good visualization to explain the concept. The outliers and the far outlier and the far outliers are defined using the quartiles and the interquartile range. So let's look at this data. We go from 1 to 10, and then we're adding a 20 and a 30. Let's compute the quartiles manually and assign them to values. So we have a 3.5 as quartile 1, we have a 6.5 as a median, and we have a 9.5 as quartile 3. Right? Remember this for a moment. And then we compute the interquartile range as quartile 3 minus quartile 1. And now if we plot this, then we see very nicely where the box whisker chart is. We see the quartiles, and we see the near threshold and the far threshold, and they are defined as quartile 3 plus 1.5 times the interquartile range for the near outliers, and for the far outliers it is quartile 3 plus 3 times the interquartile range. And the 20 is above the near threshold but not above the far threshold, and the 30 is above the far threshold as well. Right? And you see that the upper end of the whiskers is back here at 10, right? So again, they were dropped because we show them, we classify them as outliers, but then we assume we remove them, and that gives us a lower upper end of the box whisker chart. Okay, so this is the basic method. This is how it works. Remember, Q3 plus 1.5 times IQR and Q3 plus 3 times IQR, right? So we have the near outlier is above Q3 plus 1.5 IQR, and the far uses 3 IQR. All right, I need to speak out a big caveat. The box plot should not be used on skewed data. And a lot of data is skewed. With skewed distributions, meeting those outlier thresholds can happen very easily. And as an example, I give you, for example, the Democratic percent result from the 2016 election data. We have already looked at it in session 2 in the homework. So let's look at this. The Democrat percent is in the 5th column. So let's load the 5th column, go through the same computation, right? I'm just copying this computation. Let's compute the quartiles, the interquartile range, and now let's display it. And you will see that we have like, what is this, hundreds of points piling up the moment we are using the near outlier threshold. And you see that the upper whisker goes all the way into near, right? You see that this gray bar here goes all the way up to the threshold. Unlike here, where we have a sensible use of the box whisker plot, where it stops far below the near threshold. Here it goes all the way up to near, and then we have like hundreds of observations here. So we would think, oh my gosh, there is a ton of outliers. There is so many counties that have so many high points, so many high percentages for the Democrats. But in reality, it's really just a skewed distribution, right? There's nothing wrong with this distribution. It just has a skew. And would we call them outliers? I don't think so, right? They're not outliers just because we have a tail here. It's part of a skewed distribution to have a tail. So here, doing this quartile-based reasoning for cutoffs is totally wrong. We shouldn't be doing that. And if you read more of this type of literature, you will see that pretty much everyone agrees it's statistical malpractice to use the box plot on skewed data, right? And I think this is an example. All we have here is a legitimate skew, a legitimate tail, and in the box plot we see them as hundreds of observations piling up above the near threshold, and the upper whisker going all the way up to the near threshold. So this is the wrong thing to do. In my personal opinion, the box plot can be thought of as a subfunction of the histogram. I think of it like a data summary, with most of the middle information removed. The box plot is designed to accentuate extreme data according to definitions related to quartiles. But if you know your data has a lot of observations that would exceed these quartile-based definitions, then the box plot is pointless to use. In fact, it's misleading. Yeah? So keep this in mind. Here, it's not suitable to use it, but in many cases, it is. When the histogram doesn't show you anything skewed, then I think it can be a good idea to go forward with the box plot. It gives you a great summary based on quartiles. And my recommendation, always look at the histogram first. Think of it as a quick, at-a-glance, non-parametric overview. And if then the data is not skewed, then I think the box plot may be a very suitable next step. It gives you a quartile summary. And if the data is skewed, then don't base any decisions on any box plot derived outliers. All right, so next comes the distribution chart. It displays a distribution chart with a distribution symbol for each data item. So using the same list that we had at the beginning, where I had added the 32 and 33, we can clearly see in the distribution chart where the meat is, right? The numbers 1 through 10. The distribution, here is where we have the meat. Here is where we have some center. Here we have some substance. And then for a while comes nothing, and up here we have the numbers 32 and 33. So it's a very simple way to detect the outlier. It's a very good visualization to show us where something is out of the ordinary, where something violates a distribution that shows us where the center of the data is, right? And I think we'll see more in the examples now that I'm going to show you, but I think this is already a quick diagnostic way to see where the outliers are. I personally think it's ugly, but I think it did its job. It detected the outliers, right? As a scientist, you should be interested in diagnostics and not necessarily in producing beautiful business charts. And in the following, I will be taking some examples from the companion website of the book, The Elements of Statistical Learning, written by Hastie, Tip, Shirani, and Friedman. I think it's a great book for the advanced data scientist. It's probably a bit over the top for the beginner, but I still think it's a great book. And if you get it, I think you're making the right decision. Eventually, as you advance to become an advanced data scientist, you will be able to use it more and more. So I'm not going into all the advanced mathematics there in the book. It's a big book, I think something like 350 pages. But they have a companion website where they're storing the data for download. So I'm picking some of it for the analysis that I'm showing you in the following. So let's begin with the ozone data for Los Angeles. This data is pretty old. It's from 1975 or 1976. So we're reading it in with the import command, and let's look at the headers that we have here. We have the ozone level itself, and this is the target variable. Right? It's always important to know what are your predictors and what is your target variable. So the first variable here is what we're after. This is our target. And then we have several predictors, several other independent inputs. We have the Vandenberg Air Force Base 500 millibar height, that is VH. And to give you a comparison, 500 millibar is about 18,000 feet. 700 millibar about 10,000 feet, 850 millibar is about 5,000 feet. For reasons that I cannot get into, mostly historic reasons, pilots use an altimeter that is really not measuring altitude. It measures a pressure level of the air. Technically speaking, an altimeter is just an aneroid barometer. So you really are looking at pressure levels when you're looking at an altimeter. So that's why this is called the 500 millibar height. We have a wind speed in miles per hour. That's also all today in aviation. We're using knots, not miles per hour. We have a humidity percentage. We have a temperature from the Sandburg Air Force Base. We have an inversion base height We have Dago, pressure gradient, inversion by temperature, visibility, and day of the year. So let's look at them individually in a graphic form. The target variable should always be a straight line. And I don't consider it trivial to plot, because if it doesn't give you a straight line, it tells you something is wrong. Right? So it's still a good check to check something trivial. That's what unit tests are based upon. Even a simple unit test, if it suddenly fails, then something is wrong in your code. So still display it and see if it gives you a straight line. So here we have Vandenberg, here we have the wind speed, and notice that we have an outlier here, a value of 21 that we'll be looking at in a moment. We have a humidity plot, we have a temperature plot, and you can see that temperature and ozone are probably correlated. The inversion base height, not that several points are piling up here at 5,000. Dago, IBT, visibility, and day of year. Okay, so let's look at the box whisker chart, and we immediately see some problems here, right? When you display all these data sets that are not on the same scale, then we are basically getting one or two that may look reasonable, but the other ones are crushed. We cannot really see anything else here, right? This here looks like I think a 1950s lampshade. This one here looks like a drone or a flying saucer, and everything else is crushed. We don't see anything. So we'll have to look at them individually, which we're gonna do in a moment. But the box whisker chart has good methods for styling. We can give it legends, style numbers, and configure it. But still, the problem is the data set we are trying to analyze here are not on the same level, or not on the same scale. So we have the strawn up here and the long bars in 6 in this strange light, squashing everything else. So we have numbers for wind that are smaller than the whole range of others, right? So let's look at that. We have a wind number of 21, and that's much smaller than the ranges. In column 2, we have a range of 630. In column 6, we have a range of 4,900, right? If you look at this here and this here. So no wonder that some things are getting crushed. They're just not comparable. So what do? We have to plot them individually. So let's do that. And then we always should look at histogram. I think I mentioned this already. And then I think things can become a bit comparable. So I'm showing you a histogram in the left column and a box whisker chart with outliers in the right column. So here we can see now when we have something skewed, like here at the Vandenberg height, we're getting these false outliers here, right? And I think the histogram gives us a good idea of what the data looks like. It's a good summary in itself. We have the wind information here, and look at our wind outlier here, the number 21, right? It's even a far outlier. Look, it's gray. If you look closely, here's one that's black and here's one that's gray. So this is a far outlier, and I think a legitimate outlier. And then next step, you should look at the histograms. They give you a good idea of what your data looks like and where the center is, right? So in the middle, is it on one side, the inversion base height here, we see tons of items piling up at 5,000, and the other highest group here, the lowest and the highest, they have about as many elements, right? You have less than 1,000, the same, almost about the same amount as those 5,000. So there's clearly something wrong here. And look at them in detail in a histogram. Let's look at this also in a distribution chart. And again, here I don't think they're particularly pretty, but I want to show you again, you find styling options, and you can sometimes find something outlierish. These forms look strange, right? They stick out and they give you an idea where something could be, but still we are crushing a lot of elements, right? We are crushing. We have here this UFO, and we have, it's something on a big range, almost 6,000 in height here, and others crushed. So I think this is the wrong way to look at it. But when things are on a comparable level, I want you to understand that we have some very good styling options. I personally like the histogram density. That's the second plot here. And I also like the glass quartile, where you can specify how many quantiles you want. I find these displays very useful, but you cannot just throw all data sets into it. And I made a note here precisely. Yeah, look at this, right? When the data card, when you look at it, you can hover over it, and whenever you go from one section to the other, then it shows you the percentage level, right? So here it says 60%. Then I go further over this. Again, I get a small data card with 5 items. I go to the boundary, I see a percentage level, right? I find this incredibly useful. You don't find any other computer system that gives you so much interactivity. This is an interactive thing here, right? I don't have to compile something, run something, look at big plots or printouts. No, I can interactively explore this and see what I get, see what I have. So that saves you a lot of time, and you can make quick changes and instantly look at results interactively. I think this is incredibly powerful. Okay, but here we have the same problem, data on different scales. So larger scales crush the smaller ones. So here as well, we have to look at them individually. Okay, so let's do it. Let's loop over this. And I think now things are becoming a bit more meaningful. Now things are not on incompatible scales. We can now clearly see where we may have outliers. Vandenberg height has very few on the downside. The wind has, you remember the 21 up here. So you see graphical shapes that the distributions, that's why it's called distribution chart, that show you where you may have distortions in your data, and the shapes themselves tell you a story, right? This shape here tells me something, and the visibility shape here as well. So I think the distribution chart is very, very useful, very pragmatic if you display each data set on their own. And also show you this as a histogram density. I also like this one to see here. You can even see the outlier and wind much better, right? Because we get a box that has a size of 1. Up here we don't see much, right? Here we see just a thin line, but here we see, look, there's actually a measurement. There's a 1, and then the other ones here are zeros, and then here as well the weight is the center of the weight up and down there. So these shapes really tell you a story, and they tell you where you have the biggest concentration of your data and where you may have outliers. And the glass bricks, yes, here as well, right? You can just look at the sections, the cutoffs between the quantiles, and the outlier here gives you a big section. Look at this long section, that's a 21, very long section, so here's an outlier. And in the Vandenberg height, we've seen this before, here's an outlier. See at this big section here down below, we had already seen that here. So these diagnostic plots tell you a story about your data, your distribution, and makes it easier to spot the outliers. And also clearly shows you where there probably are no outliers. Temperature here, look at this. I don't see much of an outlier here, right? So I think this is a good way to look at this. All right, let's proceed. You remember from the last sessions, I've showed you query, operator form, and function composition. And here I'm using all of them in one, right? Here is a query, and I'm using an operator form, and I'm using function composition. And if you want to show these numbers, you remember you have to put them in a list in the query. And here we see that the length is 330 observations that we have. The maximum is 5,000, but the number, right, length counts the number of elements that are larger than 5,000 are 95. So that's a pretty big concentration. 95 out of 330 are 5,000. And exactly 5,000, right? Because 5,000 is the maximum. It's not above 5,000. 5,000 is the maximum value. And 95 of them are there, right? So there's clearly something strange here. And to keep the data, let's keep this on a separate. I sometimes like to start a new small window and always keep it on top here, so we can look at it always on top. And let's look at IBH, the inversion base height. So what we can see here is that tons of observations pile up on the 5,000 here, and I mean that's clearly a problem. And how to reason about that is, as I already said at the beginning, that's a matter of the judgment call. Can you remove them? Can you not remove them? And I don't want to go into the details here. I certainly have an opinion about this, but it can change very much. It depends on if the points are above or below and what the other points are doing it. Here in this case, I see a bit of a triangle coming down here. And then we have tons of points above 5,000. So there are many reasons for that. How do you measure everything above 5,000? The measuring equipment in the 1970s may not have been able to go above 5,000. And how much precision do you have that? If it were 8,000, well, can you really tell it's 8,000? Maybe it was 8,200. And the measurement equipment couldn't differentiate enough. So all I'm pointing out here is the detection of these outliers, what to do with them. If you want to remove them or you want to change something here, that's then a judgment call, and that's not the part of this session. There are some methods to include that. Mathematica has the truncated distribution, truncated distribution, and they may help you with that. However, we cannot go into this, and it may be the different decisions in different cases. Here we may say remove them. I have a medical example a little bit further down where I think the data should not be removed, right? But keep in mind, you still need to do judgment call at this point. At this point, I'm just pointing out there is a problem. There's a big problem in your data, and how you deal with that is a different matter. Sometimes removing them is the right call. Sometimes modeling it, perhaps with a truncated distribution, is the right way. But that's not for today, that's for another session. Okay, next I want to point out, the query is a great way to show a list of items that are of entirely different natures, entirely different types. In this case, we have an integer-based list here and here versus actual data. The max comes from the actual data, right? And I think that's an important thing to recognize, because very often in a list we expect data of this very same nature. This is not necessarily so, because we can put pretty much every operator here and we can create operators from functions. I could also look at the median and the mean, for example. So this comes directly from, these three come directly from the data. The first and the last do not, right? They're just counting how many data elements there are, and here how many data elements there are that remain after the select. And we can use much more here. We can make them real numbers. And here I specify this only for these two. If I did it for the whole thing, if I used and for everything, then everything now is a real, although these two should be integers, right? So again, get familiar with the functional notation, function composition. It's incredibly useful. Okay, this footnote, I said this already. Okay, the next idea, I had already mentioned central feature. The next idea is to ask the question, does the center of the data change if I remove these outliers? So I'm asking for the central feature of column 6. And I'm also asking for the central feature of column 6 if I remove these. And we can see that the central feature has changed. It has changed significantly. Have a look at central feature in the help browser. Also very useful function, and I recommend you spend some time on it. It's very well documented. It's another help browser page that I like very much. Go through it, have a look at it, and you will find out what the central feature is, how it works. And here I find it incredibly useful because you see how the central feature changes when we remove all these numbers that are 5,000. That doesn't necessarily mean you should remove them, but you see it's an important item to look at, right? Because removing them changes the central feature so much. Okay, we haven't covered find anomalies yet, but I still would like to throw it at this data at this point and see what we're getting. I'll cover find anomalies in detail in the next session, but we can already see throw it in. It's oftentimes a good idea to just throw it at something. You may see something that you may not have seen before. And it correctly found 2 outliers in a different sense. The 557 is at 38, where's that here? And the 3795 was here, right? Giving us 23. So you could consider this an outlier. I personally don't think it's too much of an outlier. Just because a number is big and not together with the crowd doesn't make it a removable outlier. There can be skew in the data, right? And skew means you have higher or lower numbers that are totally legit. So this point was found by find anomalies, and I think it's a good find. I still don't consider it an outlier. All right. Okay. I think these numbers are large, but not too outliery. Yes. Large measurements are not always abnormal. Right. And now I'm showing you find clusters. And when I ask the kernel to cluster this data, you see that it created 2 clusters and one of them consists almost entirely of those 5,000s. Right. So there's clearly something wrong here in the data. This big group of 5,000 is a serious problem. Okay, it gave us a cluster for the 5,000 group, but it also has others in here. Yes, all right, the 3795 is also in this group here, right? So it's not only a cluster of these 5,000. This cluster could make a distinction like this right here, right? It may cut through this, and the cut doesn't have to be linear. So. But the preponderance is the 5,000 number, but there can also be others that are somewhat outlierish in this data set. Okay, what about the nearest neighbor approach? So let's try that. And we are getting the 21 again as the outlier. And I sometimes like to throw in find anomalies just to see what I may get out of it. Expect the unexpected, right? Just expect the unexpected. You never know where this experimentation may lead you, but we get again the 21. So it successfully found this one as the outlier. And if I use find anomalies on the data directly, not on the nearest neighbor check, we also get the 21. What about central feature? So we're computing a central feature of 5, and if we are adding the central feature to the difference between the central feature minus the entire data set, as C is the data set, we're getting a list that has the outlier number all the way at the top. Right? When we basically subtract the central feature from the data, or the data from the central feature, doesn't matter, then we're getting our numbers with the central feature in the middle as a 0, and we're getting the outlier up here, but we have subtracted the central feature. That's why this is a 16 and not a 21. So we're adding it back. We're getting our series with a 21, and if we're now selecting everything that's larger than maximum, we are getting our 21 back again. Okay, so for the next dataset, that is a dataset about prostate cancer, and this is also taken from the website directly. So let's bring it in. Let's look at the headers. So here we have several predictors, such as log of cancer volume, log of prostate weight, the age, several other items, and the last one is train test indicator. So that's a 0, 1. I should probably display it and update here so that we can look at this better and look at this. So when you have a 0, 1, then that can be an indication that the data set was used for neural network building. Somebody tried to build a classifier, and we have an indicator here for train and test. But the point is, we have these inputs here. And for LBPH, I want to point out we have again the case that a lot of stuff is piling up here at a lower limit, minus 1.38. And as we look at them, there is some ordinal data in it. And the outcome is LPSA. And again, we get a straight line here, right? So this tells us that this is the target variable. Okay. I want to focus a little bit on LBPH, where we have the same problem. Okay, so let's display them again as histogram and box whisker chart. And here I think it's still legitimate to look at the box whisker chart. We don't have too much skewed data in it. Everything looks somewhat symmetric. This is LCA1 looks somewhat symmetric. L-white looks somewhat symmetric. I see no skew in this data. So I think these outliers here are legitimate. We have 2 points above, we have 1 below. So I think this is a legitimate use of the box plot. And age certainly has a skew when it comes to prostate cancer. Younger people don't get prostate cancer. You see that it ends here at 40. There's very little between 40 and 50. The bulk is between 60 and 70. So I think you could say this is skewed, so these outliers here on the downside don't count. I think that's debatable, but I think that could be an acceptable argument. But everything else, I think, doesn't look too skewed, so I think the box plot here is legitimate. And if we continue on to the distribution chart, again, we see strange shapes, which is, I think, good and diagnostic, but again, we are crushing too many things. These spacecraft here hover up in the air and are distorting everything. So it's better to look at them in detail. And here I think the shapes are much more meaningful. Here the shapes really tell us something. We can see where we have a weight concentration and where things are beginning to thin out. I think here this is legitimate. Again, I like to look at these shapes, but not in isolation, also together with a histogram density. I think this is a rather meaningful plot, because here we're also getting the numbers in each of these brackets that we can then look at interactively with a hover. I think the histogram density is probably my favorite chart element function in the distribution chart. And we can also do it as glass quantiles. I also find that quite useful, where we again can see, look, this is what it looks when there is no skew, right? The data was pretty much constant, so we have it's symmetric, and we have about the same sizes of these subregions. Age is skewed. Look, we have a big one here. LBPH is very skewed, right? This is all these items here at minus 1.38. So this is a problem. LBPH definitely is a problem. But others, I think, can look quite reasonable. So the min-max, the minimum is minus 1.38. And here I'll do the same comparison. I look at the length. We have 97 as the total dataset length, but 43 of them, that's quite a chunk, is really on this lower level, right? The minimum is minus 1.38, and if we're selecting everything that's less than that, then we're getting those 43, and this tells you that there's definitely something wrong here. This is 43 measurements here, and it's only 97 in total. So this is something you have to deal with. Again, we have 43 out of 97 here, and this is not good. We have a problem here. So then I looked at this closer. I know that this is the log of a measurement, right? It's the log of BPH. And then I've looked at what does it give me if I raise it to the power of E, and I get a quarter, right? So I claim that the amounts of benign prostatic hyperplasia less than a quarter couldn't be measured, right? There was just no measurement equipment, or for other reasons it couldn't be measured. So they simply called everything less than a quarter, right? And it may really be the best they could do, right? This is not criticism, but it tells us that there's something wrong. And again, we could perhaps go into modeling it with a truncated distribution, right? We have this great truncated distribution function in the kernel. We could go into that, but no, this would be more the modeling part, and that's not what I'm concentrating here today. The modeling of data is a completely different topic, and I think I would have to introduce that very differently. So here we're just looking at the outlier. So there's definitely a problem, and we have to take care of it, right? Either model it correctly, perhaps with a truncated distribution, or talk to other researchers on what to do with these outliers. But that is the reason, right? The measuring couldn't go below a quarter, so the log of it gave us this minus 1.38. Okay, so if we now run find anomalies over this data, we find that we have 0.58 and 0.27 in this data. I don't find this too meaningful at this point. I think we can skip this. This find anomalies didn't tell me too much. But let's look at central feature. So if we look at the central feature of this data, again, this is the fifth column, right? This is LBPH. We get 0.3. And if I remove all these items, we get a much larger central feature. It's at 1.5, right? So that was quite a change from 0.3, which is somewhere here, somewhere in the middle of this data set. And if we remove all these guys here at minus 1.38, we're getting 1.5. So that looks like a reasonable center of this cluster. Okay, and if we use find clusters, we see that find clusters gave this minus 1.38 a cluster of its own, right? Here we have its own cluster. Again, that doesn't mean you have to remove it, right? But in order to detect the change in the central feature, I have to remove it. And then this only allows us to conclude that we're having a big problem here. Not remove it, but it's verification that we have a big problem here with this data. Okay, the next I'd like to show you the heart disease data for South Africa. That's also on the website. And here I'm not going to go into this detail. I want to show you something else, mostly about skew. I think this one we can close now. And we have a couple of predictors that go into this model that could be built with it. Predictors in this data set. We have systolic blood pressure, we have tobacco, we have cholesterol, family history, alcohol consumption, age, and then the response is the last one, CHD. The response is coronary heart disease. And again, if we look at this plot, then we see here CHD, the last one, is 0 and 1s, right? So this is a binary variable. There's zeros here and there's 1s. So again, I suspect this was probably used or is intended for use for designing a classifier neural network. But what I want to show you here is that very often you have skewed data and you cannot immediately consider things outliers. So for example, if we look at SBP, there's a little bit of a lower limit available here, and then there comes a concentration of data, and then to the upside it's thinning out, right? Same with tobacco. 0 is the lower limit, then comes a lot that's coming immediately above it, and it's thinning out. But these numbers here, they are not really outliers. I wouldn't call them outliers, because there are people that do consume a lot of tobacco. Same with alcohol, right? It starts at 0. Then there's a lot of people that drink a little bit of alcohol, and then it's thinning out. But the top numbers here, I don't consider them outliers. Some people really do drink a lot of alcohol. Similar with age, right? You don't get cancer when you're too young, at least in most cases. It seems to be beginning here at 15 years. And then it's getting a little bit denser in the upper age range. Similar with obesity. We have a bit of a lower limit, and then comes a section that has all the weight in it, and then it's thinning out. And I don't see outliers here, right? I see a few numbers that are a bit higher than the center or below the center, but I don't see any real outliers in this, right? So that means this is skewed data, right? These shapes, when you have a center and it's thinning out to one side, we have skewed data. So I won't even show you the box plot, right? As I said, it's people put the box plot on everything. The moment they have data, they use a box plot. But you shouldn't really spread the box plot over all your data, just like you might be spreading ketchup over everything. So I'm not even going to show you the box plot here. Otherwise, I would violate my own ketchup rule. So let's only look at the histograms. And we see that this data is skewed, right? SBP, tobacco, LDL, obesity, alcohol. Age has a bit of a skew in it, right? So don't use the box plot. And the next data set that I want to use is the 2016 presidential election results by county. I've already used that in session 2, where I gave you some homework. And here I want to focus on rows 2 through 6. So row 2 is the total number of Democrat votes. Column 3 is the total number of Republican votes. 4 is the total votes. That's the sum of columns 2 and 3. And then we have the percentage result for the Democrats and the percentage result for Republican. And these are the only columns that I want to focus on here. I think the other columns don't really contain all that much interesting data. So let's take a random sample. So this is what the data looks like, and I want to focus only on these columns. Those are the only ones that I want to look at. Okay, so we may have a lot of far outliers, right? So look at this, look at how this is skewed. Every one of these is skewed. All 6 histograms here are heavily skewed. And what I find particularly interesting is that the total numbers for the Democrats and the Republicans have long tails on the upside, right? On a percentage level, the same is true for the Democrats, but not for the Republicans. You can see that here for the Republicans, the percentage result, we have a tail on the left side, right? So what this means is that in most cases that the Democrat percentage result was somewhere here 20 to 40%. And then on the upside, it was getting thinner and thinner. With the Republican county results, again, I'm talking percentages here, it's the exact opposite. We have a lot of weight in the upper regions, like 60 to 80%, and the exceptions were more on the downside, right? That's getting thinner and thinner there. Okay, and if we look at this with the distribution chart, I want to point out here that, again, it can be totally misleading. You basically see nothing here because everything gets crushed by just a few numbers. If we look at these, let me show you Los Angeles. Los Angeles has 2.3 million, and this is what you see here in the fourth column. There's a dot up here and it's not even plotted, right? It's just crushing everything down so that you can't really see anything anymore. These look like, I don't know, spaceship Enterprise spacecraft, and single outliers here can totally distort the picture. So I think here the distribution chart is a meaningless thing to look at, simply because we have some really big numbers here that are totally distorting everything. So we need to look at them individually, and then it's getting a little bit more interesting. The total numbers again don't really show us anything. The total numbers for the Democrats, the total numbers for the Republicans, and then the total numbers. But percentage, we do get an interesting picture. And this tells, these two plots here show us a similar story compared to these two here, right? We have a bit of a center, and then it's thinning out to the upside for the Democrats, and for the Republican, it's a center that's much higher, and then it's thinning down for the Republican plot. This is a distribution chart that I think is rather meaningful, because we see something in these shapes here that tell us how the distribution is structured, and where the weight is and where the outliers are. Okay, the next one, yeah, that's again the same plot. You see how this is crushed. We have this 2.3 million, a dot here that isn't even plotted. It's just completely taking it apart, and that is the top row. That's Los Angeles County. But we can look at the distribution chart with some better options. Again, I like the histogram density, and here we see this in a more meaningful manner. Again, we have the top two here, and there is exactly one element in this box, right? The top one is Los Angeles County, the second one is Chicago County. Then come a bunch of zeros, and then we start seeing some weight, right? That's where the bulk of the voter data is. And for the Republicans, it's similar structure but much shorter. We have the bulk here at the bottom, and then we don't have anything that has really large number, right? The highest is a little over 500,000, and not too many, right? There's one, a two, then comes a zero. So here we have similar structure but different sizes. But again, this is the absolute numbers. Columns 2, 3, and 4 are the absolute numbers. And in the next one, let's look at the percentage results, and they're the exact opposite, right? Similar to the histogram that we've seen before. For the Democrats, the bulk is in the lower percentages and upsides are rare. And for the Republicans, the bulk is in the higher percentages, 60 to 80, and the lower results are rare. And we can also see this when we look at min, max, and median. And I want to show this together with the central feature. I think that is the best way to look at it. So we can have huge range, right? For the Democrats, it's from 4 winning votes, to 1.6 million. And for the Republicans, it's much tighter. The 590 that I just mentioned, and the lowest result is a 57. Then comes the totals, and here we have the percentages. And if we look at the mean, they're very closely the numbers of the central feature. 3192 here for the Democrat totals, 7239 for the Republican totals, 11106 for the totals. And for the percentage results, yeah, similar as what I said. It's in the lower range for the percentage result for the Democrats, and upper range here, I said 60 to 80, so it's 67% with the central feature, which is the same as we have as the median here. So the median and the central feature are very closely related. So let me make a side note on the central feature. From the help browser, we have central feature is the same as the median with univariate data when the data length is odd. And we have that, right? We have 3,141 counties in the US. And it's clearly univariate data. And when it's not odd data length, then it finds an element in the data that minimizes the sum of distances to other data points. Right, so let's look at this a little bit closer. Let's look directly at central feature and median. And range 100 is even, range 101 is odd. So what we see is that for the range of 100, which is 100 elements, the central feature is 50 and the median is 50.5, right? But for 101 elements, it is symmetric. We can have one in the middle, and then we have even lengths on both sides. So we have 51, 51. Okay, so at this point, I think I'm pretty much done with this data set. There isn't much that I can extract and analyze from that. You can now go on and start analyzing the data set itself a little bit more, but I think it's not much more that you can find. Perhaps interesting is the top 10 tightest races by totals. But now we're leaving the outlier detection, right? Now we start actually analyzing the data, which is not the subject of this session. But if you do this, then you see exactly those battleground states that you may remember from the media. It's these ones plus Florida, right? Florida was important because it has so many people. But other than Florida, you find the top states in this list are these battleground states. Those were the heavily contested states in the 2016 election. So I would say this list plus Florida. Okay, so I'm coming towards the end of this session. I'd like to point you to other nearest methods that we have in the kernel. So there are other nearest concepts. There is geo-nearest, there is region-nearest concepts. Because nearest is not just a concept of two numbers being close together. The numbers can now represent location. There can be spots on a map, or they can be on a region. And I would like to encourage you to look at all these nearest functions that are available. The k-nearest neighbor is really a concept. It's a general approach. It's not just one function. And there are many applications of the k-nearest neighbor concept that you can generalize to a map or region or into higher dimensions. Okay, so there are many more methods for outlier detection, but then they become very specific statistics implementations. And my goal in my sessions is the exact opposite, right? I want to try to explain some general principles so that you can do things on your own, or use simple checks if something that you're being presented with is even plausible, right? It's very easy sometimes to find a simple counterexample that would speak against a thesis that somebody has proposed. So I'd like to show you some of these general principles and some ready-built visualization tools that eliminate your need to wrestle with statistic functions on your own. And I think here we have the box vista chart, the distribution chart. I find them incredibly powerful, but you have to be careful when you use them, right? It's generally the tendency that the more powerful and sophisticated a tool is, the less the area of applicability. So you have to be careful that you meet the prerequisites for this. Many theorems in math start with let so and so be given, right? And that means these are preconditions, these are prerequisites. And if the prerequisites are not given in your particular case, then you cannot apply the theorem. So when you have skewed data, you can't use the box chart, right? So these are quite useful when you meet the prerequisites. And here I would like to remind you of the paradigm that I had mentioned in an earlier session. We want to tell the software what to do, and we don't want to allow the software to tell us to specify how to do it. right? That's why these powerful functions like box whisker and distribution chart are making things very easy for us, right? We just punch it in and perhaps some styling options, and we get a very powerful result, but only if applicable, right? Only if we're actually allowed to do that. We want to learn how to harness algorithms that are already there. We do not necessarily want to create new algorithms. And if you want, I can cover more specific outlier detection methods if I get such requests from you. Feel free to leave comments in the community section. But for now, I just want to show you these simple jackknife methods and the box whisker chart and the distribution chart. And part 2, which will be the find anomalies section, which will be coming in the next section. All right. So there is much more to the nearest neighbor methods, really much more. It's an entire section of its own with so many areas of applicability. They're used in optimization, clustering, regression, neural networks, and it would really be a long list. And they also fill important gaps that others don't. For example, linear least squares regression. I think I have to make sessions in the future about regression. It's just so important, and it's just such a foundational concept. You can't do neural networks, you can't do artificial intelligence without regression. But they leave some areas uncovered, and they can sometimes be filled with nearest neighbor methods. So I would like to quote you a section from the book from Hasty, Tabshirani, and Friedman. And let's look at this. The linear decision boundary from least squares is very smooth and apparently stable to fit, but it also results in solutions that have low variance and have potentially high bias, right? Look what I'm emphasizing here with the mouse. This is regression. It can have low variance and potentially high bias. But on the other hand, the k-nearest neighbors, they are the opposite, right? High variance and low bias. So they can be very complementary. Regression and k-nearest neighbors can be very complementary. And the k-nearest neighbor procedures also are non-parametric. That's another advantage. You just give it the data, right? You don't need parameters for that. So this is an important duality that I think we have here. So we need to start looking at regression and nearest neighbors. Okay, so a reminder, the outlier detection can be approached from a regression or nearest neighbor or clustering perspective. In fact, it is a specific case of clustering. We want to find inliers and outliers. That's clustering. And I'll be glad to discuss regression and NNs, and here that means nearest neighbors and neural networks, both, in future sessions. For now, this brings me at the end of my session for today, and I'm ready to take your questions.
Thanks a lot, Andreas. Let's see. Since there is no question, I guess, we could wrap up in our session. You were watching the 6th live coding session with Andreas Lauschke. You can watch the playlist of Andreas recorded videos on the Wolfram Research YouTube channel. You can also interact directly with Andreas through Wolfram Community. Thanks for watching and have a wonderful one.